Hi, I'm Benji.
Hi, I'm Max.
And I'm Josh, and in this project we investigated a real-life 1 degree of freedom force vibration system using a model of the Willis Tower made of Legos that we created. The tower is about 0.4 meters tall and we excited it using a non-harmonic impulsive force, a Lego block that was tossed into the top of the tower.
The tower behaves like a single degree of freedom cantilever beam. When the projectile hits the top of the tower, it receives the initial impulse velocity. It then vibrates freely with damping. We assume a damping coefficient, and we found the tower's equivalent mass and effective spring constant using some assumptions with these equations.
To determine the speed of the Lego block, we shot it straight upward and used kinematics to calculate its launch velocity. For the impact, we assumed the block bounced back with about 50% of the incoming speed. We used conservation of angular momentum to estimate the tower's initial velocity at the top.
We recorded the actual vibration using an iPhone SE at 240 frames per second, which slowed the motion down by a factor of 8. After converting the footage from movie to MP4, we imported it into Tracker to track the displacement of the tower tip over time. Tracker exported a data table, which we graphed in Excel to create the experimental displacement versus time plot.
Next, we built a theoretical model in MATLAB. We used the standard second-order ODE for a damped single degree of freedom system, but instead of a forcing term, we only used the initial velocity from the impulse. MATLAB then created the theoretical displacement time curve.
Initially, the theoretical and experimental results did not match all that well. However, when we adjusted the assumed damping coefficient from 0.05 to 0.1, the two plots became very close. This highlights how sensitive vibrational systems are to damping and how hard it is to estimate sometimes. Sources of the errors include the block's rebound spin being estimated from 0.5, it could also be 90%, it could have been as low as 20%. The camera probably wasn't completely parallel to the tower, and also just capturing the video is a bit weird. The comparisons show that we expect in vibration studies, the theory simplifies reality, but with really refined parameters, we could probably get a system that models reality pretty well.
This project taught us how many practical steps are hidden behind a clean vibration plot. From measuring real-world parameters to motion tracking to debugging a model, it was satisfying to see theory and experiment converge, and it showed us why engineering models are powerful, but also why they always require careful assumptions and validation.